Hello and welcome back to another episode of Math with Stone. Today we are going to be talking about power. Okay, so power, the physics definition, is the rate at which work is done or energy is transferred. Okay, so power is how much work you do divided by how long it took you to do it, and the formula can be P is equal to W over T, which kind of makes sense. All right, so I want to take a moment to think about work. Remember that work was equal to your force times how far it went, or times the distance. Okay, so let's say that you applied a specific force of 20 newtons and it traveled a distance of 400 meters. And let's say you did that in like 1 second. Versus if it took you an hour or if it took you like 30 seconds to do. Which one would have more power? Okay, so if you had the same force and the same amount of meters and it took you 1 second to do it versus if it took you 30 seconds to do it, well, if you're dividing by 30, that would mean that you would end up with a smaller number and therefore you would have less power. So you can think of it as like you could do something really quickly compared to an ant. Even though maybe you could accomplish the same time, it would take an ant a lot longer because they don't have as much power to be able to do it as quickly. Okay, so power is how quickly you can do something in relationship to work. All right, so an alternate formula is, remember that work is equal to force times distance, which is mass times acceleration times mass times acceleration is force times the distance, and then we'd still be dividing by time. Now remember, what is distance over time? That would be velocity. Okay, so an alternate formula that you could have would be any of these three. Force times distance divided by time, mass times acceleration times distance divided by time. But then remember, distance divided by time is velocity. Distance over time is velocity, so you could have force times velocity. You could even have mass times acceleration times velocity, MAV. Okay? All right, example time. We got Mario. Mario! All right, Mario is climbing up this pole. And in one scenario, he climbs up a 20-meter pole, and it takes him 10 seconds. In the next level, he decides to climb a similar, not the exact same 20-meter pole, but it only takes him 5 seconds. In both cases, he does the same amount of work because Mario, in both of these cases, fought gravity and went up this 20-meter pole. And gravity, because it's an acceleration, will involve force, and therefore work will be done. So he went up the same 20-meter pole. He weighs the same amount. In one situation, it took him 10 seconds. The next one, it took him 5 seconds. Which one was he able to do quicker? Whichever one he was able to do quicker, if you think of it like 20 divided by 5, that would be 4 in terms of his power, versus 20 divided by 10 would be 2 in terms of his power. And which one has more power? Well, this one has 4 power, that one has 2 power. The one where it takes him less time will involve more power, so 5 seconds will equal more power. And the units for power, while we're talking about this, is known as watts. Watts are the units for power. And if you think of that, it would be joules per seconds. Because, again, it would be work divided by time is equal to power. Well, work is joules, time is seconds. Joules per second is how much energy you are consuming every second, which makes sense that light bulbs are 60-watt light bulbs, although now we use LED light bulbs. They don't actually consume the same amount. They're like 60-watt equivalents, which is confusing, all right? Not getting into that. That's a whole different topic. All right, next one. We got a 200-kilogram curtain needs to be raised 7.5 meters at a constant speed of 4 or 5 seconds. What is the power required to raise the curtain? Okay, so we got to think here. What is the work that is done on this curtain? Well, this curtain is weighing 200 kilograms, and we need to raise it 7.5 meters. So we're going to be like, the work being done will be the work that is fighting gravity. And that would mean that your work would equal force times distance. The force would equal ma, and the a would be 10 for gravity. Okay? So we would have, essentially, for our work, we would have mg times d. And if we wanted to get our power, that would just mean you take your work and you divide by time. So we got mass of 200. We got gravity, which we're going to call 10 meters per second. Let's use the units. 200 kilograms, meters per second squared. A distance of 7.5 meters. And then we would be dividing by 5 seconds because we want to do this over the time interval of 5 seconds. Well, if we multiply 200 times 10 times 7.5 and then divide by 5 seconds, we would end up with 3,000 watts of power, which makes sense because if you think of it in terms of light bulbs, it would take a whole lot of light bulb energy to be able to raise a 200 kilogram curtain 7.5 meters. It's like opening a garage door. Is a lot more work done and therefore more power needed, especially if you want to do it over the course of 5 seconds in terms of light bulbs. All right? We got one more example for you before the end of this video, and this one is going to involve no actual numbers and all variables. So if you're not into that, this is more of an AP physics thing, then I would skip out now. All right, so we got a car with a mass of m drives at a constant speed, velocity v, up an incline that makes an angle theta with the horizontal. The coefficient of friction is mk, or mu. What is the work done by friction when driving a distance d up the hill? Okay, so we need to first probably draw a free body diagram here. We got the natural force natural, right here, Fn. We got a incline. Here we would have mg going down, straight down. This would be mg cosine theta. For those of you that have missed incline stuff, it's always feeling like the opposite. Normally the vertical is sine, but in this case, it's cosine. And the horizontal would be mg sine theta. Okay, so the work done by friction will be involving the part of gravity that is going and pushing against the surface, so that is going to be the cosine part. All right, so the work done by friction would then equal the force of friction times the distance that it traveled, which in this case would be m, the coefficient of friction, times mg cosine theta times distance. Now friction is acting opposing the way that this car is moving, so it would be negative because it is going in the opposite direction. The force of friction is going the opposite direction of our actual car movement. Okay? So, with that in mind, are we going up the hill? Oh, we're going up the hill. Oops. We're going up the hill. Force of friction would still be acting in the negative direction. It's going in opposing the direction that we're actually going. Okay, so that would be our work done by friction. Now, part B. What is the power output of the engine? Well, the engine is propelling us forward. You have a few different options for doing this. You could use work divided by time, and you would end up with a completely different thing. But I would recommend that you just use the formula that talks about velocity because it's a little bit quicker and easier to deal with just velocity. Well, the velocity of the engine would be equal to the force of the engine minus the force of friction, which is going to be equal to 0, which means the force of the engine is equal to the force of friction, and therefore we know the force of friction, that would be negative m times mg cosine theta. Notice I'm not doing d here. That would be the work done. So the force of friction is just this part. And then if we wanted the actual power, remember that power can be found with a few different things. One of the formulas is work divided by time, but another one was whenever you took your work, not your work, your ma times d over time, your d over time is really just velocity. So you could take your ma, your force, times velocity. Well, here's our force, and you could just multiply by v to get the power output of said engine. Okay, so that's going to do it for this one. Until next time, everybody, stay positive, and I will see y'all later. Bye.